And so now we have to talk about microgravity experiment design as an outgrowth of classic experiment design. Ladies and gentlemen, there is one variable that plays a critical role in virtually anything we want to study, and it's often taken for granted. Does anybody have a guess on what that variable might be? A variable that plays a
Gravity.
role. I'm sorry?
Gravity.
Yes, it's gravity. Gravity plays a role in virtually anything we want to study. Let me give you two concrete examples, and this is kind of a rolly chair, sort of like oh wow experience. Because you ever watch a video and all of a sudden you watch a movie and all of a sudden the character has just realized something, which is good or bad, and the camera just either pans into them or pans back, and it's sort of like that emotional moment. You know where I'm coming from? Like too much coffee, right? So I'm going to use my rolly chair for this emotional moment, okay? Even a germinating seed knows about gravity, because when it germinates, the roots go down, the shoots go up. It's called geotropism. Even a germinating seed. Whoa. Do you see how the rolly chair works with that? No? Okay, all right, never mind. And your body knows about gravity in myriad ways. I'll give you one example. Every time you take a step, your bones are compressed under your own weight. And it sends a bioelectrical feedback signal back to the body saying, keep making those bones. Bones are really good. But in an environment where gravity doesn't exist, can anybody name an environment where gravity doesn't seem to exist? Anybody? Have you ever watched videos and seen people in an environment where gravity doesn't seem to exist?
Like
Well,
the
there's
zero
the
G
illusion that it doesn't exist in space, although it does still exist there.
Aha. So
A roller coaster?
you're digging down you're digging down in a very sophisticated way. Let me change it to say, has anybody ever seen a video of people in an environment where gravity seems not to exist?
In a really
Zero
fast
G
elevator
test?
What?
or a plane
The
that
zero
dives?
G test?
Yeah.
The KC-135 vomit comet? Yes. Can you name something else that's more that's found more on YouTube?
Zero G flight?
I'm sorry.
Skydiving?
Have you ever seen astronauts? Have you ever seen astronauts in the space station or the space shuttle? Have
That's
you ever
free
seen a
fall.
video of an astronaut? What are they doing?
They're free falling.
They're floating around. They're floating around as if gravity does not exist. It's as if gravity is turned completely off where they are. We call that a weightless environment, okay? And so the idea here is, and what was I saying? So, okay, so let's say you want to understand the role. Okay, so I was going back to that example. So, in a weightless environment in space, there seems to be no gravity, which means there's no bone compression, which means there's no signal back to the astronaut's body saying, keep making those bones, bones are good, which means the body starts excreting the skeletal system, which requires the astronauts to have pulleys and straps to compress their bones to minimize bone decalcification. Gravity plays a role in virtually anything we want to study. Does everybody understand what I just said in terms of those examples? So let's say you want to understand the role of gravity in that or this or that thing down there. You want to understand the role of gravity in something. What needs to be the independent variable that you change?
Force.
I'm sorry?
Force.
The force of
Gravity.
gravity. You've got to change gravity. If you want to understand the role of gravity in something, you have to change gravity and see what happens. It's classic experiment design, right? If you want to understand the role of an independent variable, particular variable coming from the essential question, you've got to change that variable and see what happens. Well, the essential question that drives all microgravity experiment design is, what is the role of gravity in this, that, or that thing over there? Which means you need to change gravity. How do we change gravity?
You put it somewhere where gravity that seems not to exist.
You put it
Free
somewhere
fall.
where gravity seems not to exist. And what was the environment that we talked about before where gravity seems not to exist?
The ISS.
The
Weightless
International
environment.
Space Station. So if I bring your experiment to the International Space Station, and Casey, Lynn, get ready. If I bring your experiment to the International Space Station, will it operate in the seeming absence of gravity? The astronauts are floating around.
As
According
close
to
as
the
you can
astronauts,
get.
I'm sorry?
As close as you can get.
Yeah, it's essentially zero. Unless you throw a thruster on or you look at differential gravitational forces, because one side of the spacecraft is a teeny tiny closer to Earth than the other side of the spacecraft. But for all intent and purpose, it's zero gravity. Microgravity is a technical term. It's zero gravity. And a microgravity experiment means an experiment in a weightless environment. That's all a microgravity experiment is. An experiment in a weightless environment. So if you bring your experiment to the International Space Station, will it operate as if gravity is turned completely off?
Yes.
Yes. And Casey, Lynn, to understand the role of gravity in what you're studying, what's in that experiment, what else do I need? I have an experiment operating on the
Oh, the
International Space.
experiment.
You'll need a control. Where
I
there
need a
is
control. And where is the control going to take place?
where there's gravity on Earth.
On Earth. So when your flight experiment comes back, this experiment, from the experiment's vantage point, operated in the seeming absence of gravity. This one operated in Earth gravity, and you compare the behavioral differences in what you're studying to understand if there are behavioral differences, which will give you an understanding of the role of gravity in what you're studying. Does everybody understand how easy a microgravity experiment is? Okay, let me summarize again. You want to understand the role of gravity in something. So the flavor of essential question that we are asking for all microgravity experiment design is, what is the role of gravity in this, that, or the other thing? I need to change the gravity variable. So I have to trick the experiment. I have to bring the experiment to a place where there seems to be no gravity, so it will operate as if there's no gravity. And we run a control on the Earth at the same time. So when we bring them together, it looks, at least from the experiment's vantage point, that we've changed the gravity variable and we can do the experiment. Does everybody understand that concept? How many of you feel you now know what a microgravity experiment is? Give me a thumbs up. Okay, so you don't feel any apprehension about that, hopefully. But what came up before is that I had to change my vocabulary. I had to be a little more careful with my vocabulary, because I had to add the word seemingly no gravity. And I really want to drill down into that so you understand what's going on, okay? So here's the deal. Let's say so first of all, let me say that do any two masses in the universe attract each other with a force of gravity?
Yes.
Yes. Any two masses in the universe attract each other with a force of gravity, but you don't see these two coffee cups flying towards each other because gravity is an incredibly weak force. At least one of the masses has to be really massive for you to really see gravity in a noticeable way. Can you give me an example of two masses where one mass is really massive and you get to experience gravity. You get to depend on gravity every second of every day of your lives. Give me an example of two masses where one is massive and it impacts you directly, so that you depend on that gravity that manifests every second of every day of your lives.
Earth.
And
The moon. The moon.
The sun.
well, do you depend on the moon and or the gravitational interaction between the Earth and moon every second of every day of your lives?
The Earth and me.
The Earth and you. The Earth and you. And what's happening here is that the Earth is a massive ball. It's 8,000 miles in diameter, 12,000 kilometers across. And all of the mass of Earth is pulling on you right now. All of the mountain ranges, all of the oceans, all of the crust, the core, the mantle, the entire mass of Earth, from the mass under your feet to the mass on the other side of the planet, 8,000 miles below your feet, is pulling down on you with a force of gravity. And what do we call the force of gravity exerted by Earth on you?
The normal force.
G.
No, it's
F sub
most
G.
people. I'm sorry?
F sub G.
Okay, let me tell you that the overwhelming majority of human beings know this word, even kids that aren't even in school yet.
Weight.
The force of gravity exerted by all of planet Earth on you is called your
Weight.
weight. That's your weight. That's what that means. When you get on a scale, a bathroom scale, you're measuring the force exerted by all of planet Earth on you. And it must be a weak force, because if you weigh 150 pounds on that scale, it took all of the mass of the Earth to pull down on you with that force. Does everybody understand the basics here of physics? Okay. Intuitively, what do you think happens to the force of gravity between two masses when you increase them?
It gets weak.
Increase the distance. I'm sorry. What happens intuitively to the force of gravity? Just kind of think about it. If you
goes
increase
down.
the distance between them.
It gets smaller.
Yeah, it kind of gets
Deuces.
smaller because they know less and less of each other. So how can we reduce the force of gravity knowing this? Because the force of gravity on anything we study is its weight, right? It's operating in the gravitational field of the Earth. The Earth is pulling down on everything we see. So if I want to decrease the force of gravity, what might be a way to do that?
Send it away.
Move it away from the Earth. Move it away from the Earth where the gravity force diminishes. So let's go to outer space where there's no gravity. That's what most human beings think. The astronauts are weightless because they're in outer space. But let's look at this a second. What's the tallest mountain on Earth?
Everest.
Everest. Not tall enough. I want to find me a mountain 47 times higher than Mount Everest. And I don't know why the U.S. Geological Survey hasn't found it, but I've named it. It's Jeff's Peak. And what's really cool is that when I go to the top of this mountain, 47 times higher than Mount Everest, I'm now 250 miles above the surface of the Earth. Can anybody guess what I might find 250 miles above the surface of the Earth?
You'll still be staying on top of that mountain,
Yes.
although you might have some trouble breathing, but you probably won't be weightless.
Okay, so Ella, you're right. But my question is, when I'm 250 miles above the surface of the Earth, what object might I find up there?
The ISS.
The International Space Station. It orbits 250 miles above the surface of the Earth. And look, here I am, Ella, standing on my mountain, and the International Space Station just flew by my face. So the astronauts are at the same distance above the surface of the Earth as me. And I look through the big window on the International Space Station called the cupola, and sure enough, the astronauts are floating around. I know one of them, Don. Don says, "Hey, Jeff, how you doing? Look, there's no gravity over here. I'm floating around. There's no up, there's no down." Okay, cool. But what I didn't tell you, and I have this problem of seeing a therapist, I seem to bring my bathroom scale everywhere I go. I happen to bring my bathroom scale on top of my mountain. So here I am at the exact same distance above the Earth as the astronauts. I put my bathroom scale down on my mountain and I stand on it. And what do you think I weigh? Ooh. There's no wrong answer.
About the same as normal.
Yeah, probably
Yeah,
have a
About the
little bit
same.
of mass.
So what you're saying is I weigh about the same as what I weigh on the surface of the Earth. Is there another obvious answer?
Might be a little heavier. More mass.
Slightly lighter than you would be on the at sea level.
Maybe
No, other
so.
way around.
But there's another obvious answer when you compare what's happening to the guys right on the other side of the window from me.
You might be weightless.
I might be weightless. I could read no weight at all, so I'm floating around like them. I could weigh the same as what I weigh on the surface of the Earth. I could weigh something in between, right? Does everybody understand that?
You weigh about 0.94 times as much.
0.94. Ooh, did you do a calculation?
Yeah.
Okay, very good. See, he was silent and he did a calculation. It turns out that when I stand on my bathroom scale, I weigh about 90% of what I weigh on the surface of the Earth. Almost the same, just a little bit less. I weigh 90% of what I weigh in my bathroom at home on my scale. Now, to understand this, okay, here's the Earth. What's the diameter of the Earth?
8,000 kilometers, thereabouts.
It's 12,000 kilometers or 8,000. So let's use miles because that's a bridge to the familiar. We understand miles better than kilometers. So it's 8,000 miles across. How far above the surface of the Earth is the International Space Station?
250.
250 miles above the surface of the 8,000 mile diameter Earth. Is the International Space Station out here? Where is it?
Much closer.
Like here?
Closer.
Like
Here?
a small state of New York, like half the state of New York away from it.
Yeah, it's like really close to the Earth. It's just skimming the top of the atmosphere. It's really close to the Earth. So, have the astronauts moved far from the Earth?
No.
So, should the force of gravity exerted by Earth on them be almost the same as when they're standing on the surface of the Earth?
Yes.
Let me start with the mountain. I'm on the mountain at the same height, down here, just above the Earth's atmosphere. Ella said I'm going to have a hard time breathing. She's absolutely right. But I'm very close to the surface of the Earth. So, is the force of gravity exerted by Earth on me, my weight, almost the same as what it is on the surface of the Earth in my bathroom?
Yeah.
Yeah,
Yes.
it's just a little bit less because I've moved a little bit from the Earth. But the astronauts are at the same distance from the Earth as me, which means they cannot be weightless. They are weighted. The force of gravity exerted on them, their weight, is 90% of what they weigh on the surface of the Earth. Because the force of gravity exerted by Earth on them depends on the distance between the center of the Earth and where they are. Does everybody understand what I just said, right? I'm walking you through a logical argument why the astronauts are not weightless. They weigh the same as...
Centrifugal force.
Well, not really. Let me go to the next level. The start of this next level is to ask a really important question. Okay, so I think I walked you through this logical argument where you now believe that the astronauts feel almost the same force exerted on them from Earth as when they're on the surface of the Earth, so their weight is almost the same. Okay, I think you'll buy that. So what's the problem, ladies and gentlemen? What's the problem?
The problem is that they seem weightless even though they're not.
Yes,
They're
that's
falling.
right, Ella. Yes, what the heck is going on here? Okay, so to do this correctly, I need to take you to the top of my favorite building. I was born in the Bronx in New York. My favorite building is the Empire State Building. And somebody said something about an elevator, so let's put the elevator to use. So the Empire State Building, it's a tall human structure. Is it big? Is it a big structure? How big is it
Yeah,
compared to
pretty
Mount
big.
Everest? How big is it compared to
well,
Mount Everest?
It's
What?
small. It's small compared to Mount Everest.
And what about compared to a mountain 47 times higher than Mount Everest?
Tiny.
Really tiny. It's a tiny little thing. So if I take an elevator from the ground floor to the 104th floor where the observation deck is, okay, have I changed my distance from the surface of the Earth much?
No.
Sort of like not at all. Like it's like infinitesimal difference in altitude above the surface of the Earth. So here's the deal. I go into my elevator. The elevator has no windows. I go into my elevator. I bring my trusty bathroom scale because I have it in my backpack always. And before I get to the Empire State Building, I went into a kindergarten class and I grabbed one of the kids' chairs. And what's cool about this chair is when I stand on it, I'm a foot above the floor. Everybody picture that? In the elevator with no windows is me, a bathroom scale, and a kid's chair where I stand on it, I'm a foot above the floor. Everybody with me on that? Okay, I go to the 104th floor. The doors open up. It's as if the elevator's part of the 104th floor. I see people walking around, and I'm going to do my experiment. I step up on the chair a foot above the floor, and then I step down on the bathroom scale. And ladies and gentlemen, what do I weigh? I step up on the chair. The elevator's at rest. It's part of the 104th floor. I step down a foot on my bathroom scale. What do I weigh?
The
What is
measurement
your
on this,
weight on the regular?
Say what?
You weigh
What's your weight
less.
on the ground?
I weigh virtually the same as what I weigh on the scale in my bathroom on the surface of the Earth, because the 104th floor of the Empire State Building is really not moving far from the surface of the Earth. I would need a super duper, really high precision accuracy scale to measure the difference in my weight going from the ground floor to the 104th floor. Everybody with me on that? But you know what is the hallmark of science? Reproducibility. So I want to do the experiment over again. So I do. So I get back up on my chair. My back is to the door, the elevator door. So I get up on the chair. And the moment I walk off the chair, I'm doing the experiment over again. The door closes. I don't see that happening. The door closes and something bad happens. Somebody cuts the cable holding the elevator. The moment I walked off the chair. What happens to the elevator, me, the bathroom scale, and the elevator itself?
You're in free fall.
We
You
fall.
feel weightless.
Okay, wait. So let's walk through the logic here. We fall. What's happening to the speed of me, the bathroom scale, the chair, and the elevator?
It's accelerating at 9.8 meters per second.
Okay, so what he's saying is the speed is increasing. We say that it is accelerating. What is causing the acceleration?
The pull of gravity.
The force of gravity exerted on all of those objects. What is the force of gravity exerted by Earth on the elevator called?
the weight of the elevator.
The weight of the elevator, which means the elevator is falling under its own weight. That's where that expression comes from. Now, what fills the and so now it's accelerating. It's going faster and faster. We call that the acceleration due to
Gravity.
gravity. And somebody, I don't see it, was it Jared? I said I will say, does somebody know the number associated with the acceleration due to gravity? Jared, what is it?
9.8 meters per second.
No.
An engineer would tell you
That's
10
not
meters
what you gave me
per
is
second.
not an acceleration, it's a speed.
Oh, I'm actually not sure then.
9.8
wait.
meters per second
It's
squared.
9.8
Yeah.
meters. It's 9.8 meters per second per second.
Okay.
9.8 meters per second squared. Can anybody tell me what that means?
It means that for every second that the elevator is falling, its speed will increase by 9.8 meters per second.
Yes. So every second, the force of gravity increases the speed of the elevator by 9.8 meters per second. I don't know what that means. I don't deal with meters. I don't know what that means, but you all drive cars or take public transportation. You know what miles an hour means. The acceleration due to gravity in miles an hour is every second the speed increases by 20 miles an hour. Every second, because of the force of gravity, the speed increases 20 miles an hour. So after 1 second, how fast am I moving?
20 miles an hour.
20 miles an hour. After 10 seconds, how fast am I moving?
200. But you
200
hit,
miles an hour.
but
If
you
it's a
hit
really tall elevator shaft, if I don't go splat on the bottom, after 100 seconds, how fast am I moving?
2000, but don't you hit a maximum velocity?
Okay,
Not
so
in a
Jared
vacuum.
says, well, if it's just the force of gravity acting on the elevator, me, the bathroom scale, and the car, in 100 seconds, I'll be moving 2,000 miles an hour. The acceleration due to gravity is huge.
In
But
a
Jared,
vacuum.
what fills the shaft of the elevator?
Air.
And what does air do?
There's resistance. So it's
It
pushing
causes
it back.
it causes a resistance. It causes a drag force. So as an example, I go parachuting. I jump out of a plane. The acceleration due to gravity starts to accelerate me, but the resistance, the air drag, goes as the speed squared. So as my speed increases, the air resistance increases until finally it won't let me go any faster through the air, even with the force of gravity exerted by Earth. What do we call that, ladies and gentlemen?
Terminal velocity.
Terminal velocity. And for a human being, it's about 100 miles an hour, and you can't survive landing at 100 miles an hour. So you deploy a parachute to really increase the drag to slow you down so that you can parachute another day. Everybody understand that? Everybody with me on that? Okay, so now what we're going to do is we're going to suck all the air out of the elevator shaft, and we're going to make sure when the elevator moves down, it doesn't rub up against the side walls of the shaft, so there's no friction. So there's no air in the shaft, there's no friction. What then is the only force acting on the elevator?
Gravity.
Gravity. It's the only force left. It's the force acting on the elevator. The elevator is falling under its own weight. Jeff is falling under his own weight. The bathroom scale is falling under its own weight. So is the chair. And so is there anything that's going to stop the acceleration until you go splat?
No.
No, you'll keep accelerating. Okay, that's an important point. What do we call the kind of falling where only gravity is the force operating?
Free falling?
Free fall, because it's free of all other forces. If only the force of gravity is acting on an object, it is said to be in free fall. So now here's the question. When the cable is cut, me, the bathroom scale, the chair, and the elevator start accelerating down under our own weight. Are we all accelerating down together? Is it the
Yes.
same acceleration for me, the
Yeah.
bathroom scale, the chair, and the elevator?
Yes.
Anybody not sure? Kind of go like this if you're not sure. Okay, so let me explain this, okay? I'm a really big guy. I've been working out, and I hold in one hand a Toyota Camry. Got that? I'm holding a Toyota Camry in one hand, and in the other hand, I'm holding a bowling ball. Well, the Toyota Camry is a lot more massive than the bowling ball. If I drop both from the same, if there's no air resistance, so they're in free fall. If I drop the Toyota Camry and the bowling ball from the same height at the same time, will they hit the ground at the same time?
Yes.
Tracy, what do you think? Camera and bowling ball, you're not sure, right? Okay, so let me do this. The mass of the Camry, is that the equivalent of a certain number of bowling balls? The mass of the Camry, can you think about that mass as maybe 460 bowling balls? Right? So instead of dropping a Camry, a Camry is a car which is much more massive than this bowling ball, I'm going to turn the Camry into 460 equivalent bowling balls because that's the mass of a Camry. Now I'm dropping 461 identical bowling balls from the same height at the same time. And if I'm dropping 461 bowling balls from the same height at the same time, will all the bowling balls behave the same and hit the ground at the same time? They're all the same bowling balls. I could take the 461 bowling balls and give them a little space between each other. So I'm dropping 461 identical bowling balls from the same height at the same time. Will they hit the ground at the same time? What do you think? They have to, because they're all the same. What one bowling ball does, all the other bowling balls have to do, which means that the Toyota Camry and the bowling ball will have to hit the ground at the same time if you drop them from the same height at the same time. And that's why the acceleration due to gravity, 20 miles an hour 20 miles an hour increase every second, or 9.8 meters per second, does not have anything to do with the mass. It has nothing to do with the mass. Everything under the action of gravity falls with the same acceleration. So now let's get to the secret sauce, and you got to kind of follow me really carefully. The cable is cut the moment I'm walking off the chair, okay? And all of a sudden, there's no air in the shaft, there's no friction on the sidewalls. All of a sudden, Jeff, the bathroom scale, the chair, and the elevator car are in free fall, accelerating together, okay? If Jeff moves down 100 feet in a certain period of time, will the floor of the elevator also move down 100 feet in the same period of time? If everything's accelerating together, if Jeff moves down 100 feet in, say, 10 seconds, will the floor of the elevator also move down 100 feet in 10 seconds?
Yes.
Yes.
Everybody with me on that? If everything is accelerating down together, if I move down 100 feet in 10 seconds, the elevator floor is going to move down 100 feet in 10 seconds. Where was I in the elevator when the cable was just cut?
You were
Where
a
was
foot,
I? I'm sorry?
you were a foot above the scale.
I was a foot above the bathroom scale, a foot above the floors, walking off the chair. But if I go down 100 feet in 10 seconds, is the floor going to move away from me 100 feet in the same 10 seconds? If I go down 100 feet in 10 seconds and the floor goes down 100 feet in 10 seconds, well, if I move 100 feet in 10 seconds towards the floor of the elevator, is it true that the floor of the elevator in the same period of time is going to move away from me 100 feet in 10 seconds?
Yes.
Can I catch the floor?
You shouldn't be able to.
I can't catch the floor. What do I see in my elevator?
Everything's floating.
I'm floating a foot above the floor. I can't catch the floor. I did the experiment over again. The first time it was great. I got up on the chair, I stepped down on the scale, I weigh almost the same as what I weigh on the surface of the earth. I wanted to do the experiment over again. And now, unbeknownst to me, somebody cut the cable the moment I'm walking off the chair. And now we're all accelerating down together. I can't catch the floor. I'm floating in the middle of the elevator. I look around and I say, who turned gravity off? There's no gravity here. Can I see the floors of the Empire State Building rushing by me at an ever-increasing speed?
No.
Yes.
Why? Why can't I see that?
Didn't you specify that the elevator doesn't have any windows and the doors
There's
closed?
no windows. There's no windows in the elevator. I'm in the elevator. I step down on the scale. I weigh the same. I try the experiment over again, and now I'm freely floating a foot above the floor. I can push off this wall and float to the other side. I can push off this wall and float to the other side. I can push off the ground and rise to the ceiling. I can push off the ceiling and go to the ground. I am weightless. At least I seem to be weightless. And here's the irony, ladies and gentlemen. It is the force of gravity exerted by this that is causing me, the bathroom scale, the chair, and the elevator car to plummet at an ever-increasing speed. But inside a freely falling laboratory, everything will behave as if gravity is turned completely off. Does everybody understand the logic behind what I just said? Now, this is all on the website, so you can kind of ruminate over a cup of coffee or something, some beverage, okay? But the point is, as soon as you're in free fall, everything is freely falling together. And that allows you inside that laboratory to experience weightlessness. Now, if there's no air in this room, and I drop this ball, is it in free fall? If there's no air in this room, is gravity the only force acting on this ball?
Once you drop it,
Yes, once it leaves my fingers, right? The only force acting on it is gravity. So it's in free fall. This is the elevator. Let's say I throw it with a little force. I push it with a little force, which accelerates the ball up to a speed, and it leaves my fingers with a certain speed. Can somebody describe the trajectory? What's the path it takes when I throw it like this and it leaves my fingers?
Parabolic.
So it arcs and it hits the ground. If there's no air in this room, once it leaves my fingers, so I'm not pushing on it anymore, what's the only force acting on it?
gravity.
Once it leaves my fingers, the only force acting on it is gravity. So is this in free fall? If there's no air in the room? It's not. So Casey Lynn says it's not in free fall. Free fall means that the only force acting on an object is gravity. Once it leaves my fingers, a force, by the way, is a push or a pull, right? Gravity pulls down. I could push like this. But once it leaves my fingers, I'm not touching it anymore. I'm no longer pushing it. I'm no longer pulling it. Once it leaves my fingers, the only force acting on that ball is gravity if there's no air in this room, which means this would be in free fall. If I throw it a little faster, what happens to the trajectory, the path?
It gets longer.
It gets farther and it hits the ground. And if I keep throwing it faster and faster and faster, what happens to the path?
It keeps getting longer.
It keeps getting longer until the point is reached where I throw it really, really fast. And as gravity arcs it, it goes completely around the Earth, never hitting the Earth. And in 90 minutes, I can catch it from the other side in my hand. If there's no atmosphere around the Earth, if I throw this ball at 18,000 miles an hour, it will be in free fall once it leaves the rocket, and it'll make such a big arc that it will swallow the Earth and come back and land in my hand. This is the elevator. This is the International Space Station. The International Space Station is in free fall. It's a freely falling, continuously freely falling laboratory. And everything inside it will behave as if gravity's turned completely off. And the force of gravity is alive and well at that altitude above the Earth because it's causing the International Space Station and the astronauts to fall around the Earth instead of flying off into deep space. Does everybody understand how I got to this point? Okay, so
I'm a bit confused. So at that point, whenever you're up there, gravity kind of like works in a horizontal manner instead of downwards.
actually, no, the gravity force always acts towards the center of the Earth. And if I had a whiteboard here, I could show you the vector diagram where when the space station is going this way, and when there's a force pulling it towards the center of the Earth, it causes the new vector to be this way. And so the pull towards the center of the Earth is constantly changing the displacement vector. So it's causing a circular path, and the force is directed towards the center of the Earth.
It's kind of like if it was on a string being like twirled around the Earth.
That's exactly right. So there,
Okay.
that's good. That's good. So with regard to what Silver said, that string is pulling down towards the center of your hand, and it's causing it to go around in a circle once you give it a horizontal speed to start it off. Okay?
Yeah,
So
got it.
everybody understand what we got, how we got here? Now let me make it really simple for you. Remember, I told you what classic experiment design is all about, and I said that a microgravity experiment is an experiment in a weightless environment where gravity seems to be turned off. But the idea behind a microgravity experiment is that you want to understand the role of gravity in something. And so you need to change gravity and take the experiment to the International Space Station where it is in free fall, and you run the same experiment on the ground on the surface of the Earth, and then you compare them when they come back down. For you to understand that little storyline, do you need to understand the mountain? Do you need to understand the elevator? Do you need to understand the ping pong balls? No, not really, because that was only to get you to a point to understand why the astronauts are seemingly weightless. And now you understand that if I bring a microgravity experiment to the International Space Station, even though gravity is alive and well up there, because it's a freely falling laboratory, it will behave as if gravity's turned completely off. Does everybody understand what I just said? Okay, so if you want to forget the mountain and the elevator and the ping pong ball, be my guest, okay? But I wanted you to understand why the astronauts are weightless and why you would do a microgravity experiment there. Everybody with me on that? Okay, so that was the long conceptual thing, right? Take literally a 5-minute break because we still have 3 things to cover, which are nowhere